Okay, we're good.
So we're good? It's going to cut my head off the whole time, but that's okay.
That's okay. Do you want your hand?
No?
Just crouch the entire time.
Madison has asked for number 11. All right, so 2 things you can do with this one. You could literally use the formula you wrote down, or maybe even remember that formula you wrote down, because somewhere along the line, if you were here the day we did this. We might have done an X version of it, but we can just add a U version of it. What is it? Anybody remember what it is? So, look like this. Yeah, right now. Right. That was what it was. So you could use that. I would have no problem with that. I mean, it was something I gave you. So U would be 4 theta. I'd have to multiply inside by a 4, outside by a 1/4, and I would essentially have negative 1/4 natural log of the cosine of 4 theta plus c. So you can do that. I have no problem with that. I mean, that's the whole point of giving you those. But if it were me, I probably would not have that memorized, other than the fact that, you know, I've taught this so long I have it memorized, but I would not memorize that. I would actually probably calculate it. And the way you would calculate it is by rewriting it as first sine 4 theta over cosine 4 theta d theta, and you'd handle it like any other problem we've been doing. Now, here would be a good question. What would you make U be? So I've kind of said that if you have some quantity raised to a power, then that's likely U. Now, I should probably clarify that and say, if that quantity is to a power other than 1, that would probably be what you would make U. So what would be the correct choice here? Cosine of 4 theta, because that's really raised to the negative first power. So then du would become, a little tricky with some chain rule stuff here, negative sine 4 theta times 4 d theta. So if I check what I have so far, there's my u. This stuff all has to be part of my du. Comparing it to what I have, what do I need? A negative 4. So I throw a negative 4 in here to give me what I need, but compensate the negative 1/4. So now I'm good to rewrite. I got my negative 1/4 out in front. This mess now becomes a lot simpler. 1 over u, du, right? Right, because the u is my yellow. There's my 1 over u. Everything else is part of my du. So, much simpler problem to solve, hopefully. This becomes a whole new rule. Natural log of the absolute value of u plus c. And this is an indefinite integral, so I have to substitute back in. And so, that would be it. Which, again, would be exactly what you'd get if you just used the rule as I kind of gave it to you. But good. Anything else? 15? So it's good that we are going to do at least one definite integral, since you've been doing these so much with the calculator in the last chapter. Good review. I'll say the same thing again. I mean, a quantity being raised to a power other than 1 is probably a good choice for you. So what do you think? X plus cosine x. I don't know if continuing to color code these is necessary, but I like. So there's my u. Everything else better be part of that. And again, to find du, I'm not really looking at this. This is just me telling you that all better show up here. To find du, you're simply taking the derivative of u, right? So derivative of u is, term by term, 1 plus negative sine x, right? Okay, write it minus sine x dx. So the beauty of this problem is, it's what I have, right? I don't need to multiply by anything or do anything else. So this whole thing, the yellow is just u, so there's my 1 over u. Everything else that's in green is du, and here's the part, I feel like I should at least remind you of, that, we did so much in our calculator lately, you might have forgotten that these are x's, and you can't be lazy even for one step, because here, these need to be u's. You can't mix x's and u's. They don't like each other. So, how do I find u's? Well, I take the x's, plug them into this relationship. Now, it's going to require you actually know some common values of trig. I don't think it's terrible. 0 shouldn't be too bad. You get 0, right? You're putting that in for x, plus cosine of 0. Cosine of 0? So, at the very least, right? 0, cosine is the x-coordinate, right? So cosine of 0 is 1, so anyway, 0 plus 1, 1. What about pi over 2? So pi over 2 is up here, cosine is the x-coordinate. What's cosine of pi over 2? 0, so pi over 2 plus 0, pi over 2. Right? And now this is the part I was kind of talking about before. When we were doing an indefinite integral, you had to go back, but here you've changed the problem. The answer is a number, so it doesn't matter. It doesn't matter if you do it in terms of u or do it in terms of x. So why would you go back? Because all you're going to do is make it a more complicated problem. And if you did decide to go back to x, what do your limits have to go back to? The original. So just stick with the simpler problem, because this is actually pretty nice. New rule, antiderivative. What do you get? It's the antiderivative of this. Natural log of the absolute value of u. Limits of integration, 1 to pi over 2. You're not going back. So you're just going to do upper minus floor with the u's. So I get natural log of, and it's okay if I drop the absolute value, you understand pi over 2 is positive. Right? Minus natural log of 1, again I'll drop it because 1 is positive. Be a great answer, be 100% happy with that answer. Happier if you know why I'm just going to write this. Why am I just going to write that? Because this equals 0. Right? I said, I think on Wednesday or whatever, if we were doing this, that there's only 2 natural log values you should really know. It's kind of a lie a little bit because you shouldn't, but you should know natural log of 1, 0. You should know natural log of e, 1. And why I say it's kind of a lie is because you should really know natural log of, say, e squared. But it's not a lie because that really just means you need to know the natural log of e, right? Because what we do with this 2, bring down in front. So 2 times 1, right? I guess natural log of e to the 3rd. 3. You get the pattern there. All right. Good? Anything else? Let's call. Liz, anything? No? Okay. Then we're going to talk inverse functions. Now, why inverse functions? Well, we've been doing logs, or natural logs at least. We haven't really done any other logs. And we're going to then transition, say tomorrow, depending on how things go, or maybe the next day, we're going to transition to finding derivatives and doing integrals of exponentials. And so how are exponentials and logs related? They're inverses, right? And so today we're going to talk about derivatives of inverses in general. Not just logs and exponentials, but in general, there's a relationship between the derivatives of just inverse functions. And so I thought I'd start out with, let's say, about a 2-minute review of inverses. So tell me what you know about inverses. Anything. First of all, what are inverses? Good, so the graphs, just like this, are reflections over the line y equals x. And this is really the one we're kind of been talking about. This is an exponential. I think that's e to the x, actually. And this is the natural log, and so the reflections over the line y equals x, which isn't surprising if you really think about it. If the reflections over the line y equals x, what that really means to you is if the point 0, 1 is on the blue one, automatically you know what point is on the red one. 1, 0. If the point 1, 2.8-ish is on the blue one, then on the red one you would find 2.8-ish, 1, right? So you understand, why the reflections over y equals x. That also kind of helps us understand how to find them. How do you find inverses? I kind of just gave you a hint with this whole. Right, you switch y and x. Isn't that what we were kind of doing with the numbers? And then you might have to solve it for y, depending on, but you can switch x and y. What I didn't have somebody actually tell me, but maybe you just knew this, is that inverses, why they're really important, is they undo each other. Right? What do I mean by undo each other? If you took a number, let's take a number like 127, and you square it, do you have any idea what that is? No. But if I then said, okay, take the square root of it now, you would get 127, right? Because they didn't undo each other, so you get back what you started with. And so I think that's what I kind of have up here is, what does it mean for functions to be inverses? They undo each other. How are the graphs related? Kyle told you that. They're reflections over the line of y equals x. How do we find them? Jake said switch x and y, right? The only other thing, I guess, is kind of a trick question, and I'll tell you in advance it's a trick, which I guess makes it no longer a trick. But do all functions have inverse functions? And before you answer that, let me tell you, it would be a totally different question if I crossed this word out and said, do all functions have inverses? If I said, do all functions have inverses, the answer is yes. And it's easy to do. You just switch the x and y. You can be done. But when I say, do all functions have inverse functions, that's a whole different question. Because one of the things that sometimes gets lost is, what's truly the inverse of x squared? What would it look like graphically? So, well, of x squared, the inverse graphically would really look like that, right? Which is not a function, doesn't pass the vertical line test, right? So what we do is often, and you'll see that reflected here, is often when you're talking about the inverse, you only take part of the domain. For, these inverse functions, you're really only saying that the square root of x is really only the inverse of this function for positive values, right? So, all right, let's get to the actual calculus of it. So I have a couple of pretty easy questions here, but we're going to notice some relationship. Okay, it says find f prime of 3, so I'm telling you f is x squared. This shouldn't be too tough, right? Not meant to be tough. Let's not overthink this. You would maybe start by telling me that f prime is, what is it? 2x. And so therefore f prime of 3 is 6. Didn't lose anybody yet, right? G prime of 9 shouldn't be much harder. I mean, it's a little bit tougher function. What's G prime? So you want to think of it as x to the 1/2. Still you power rule, bring down the 1/2. Would you agree 1/2 x to the negative 1/2? Yes, right, power rule. So G prime of 9, I can squeeze it in here. You are expected to know what 9 to the negative 1/2 is without a calculator. What's 9 to the negative 1/2? 1/3, right? Because 1/2 means take the square root. Square root of 9 is 3. What's the negative tell you to do? Flip it. So you get 1/3. 1/3 times 1/2. It's 1/6. Now, if we back up here for a second, I mean, that was just doing the algebra.